Thank you very much, Ken. Introduction like that, my mother would probably believe, but maybe not too many others. Thank you very much, Ken. I want to share with you a story from the past. This begins a little more than 35 years ago, and this was something that I worked on during my Air Force career. It was actually the last assignment I had before I decided to retire and move on to some other interesting activities. What I'm going to describe here today sometimes gets associated with just me. And as you'll see this project that I'm going to describe, it's very clear no one person does any of these things. This was done by an extraordinary team of people that I had the opportunity to work with over a period of about 10 years or so. And what I want to describe to you here is the stealth program, which isn't very well understood about what it is, what it isn't, how magic is this stuff, how meaningful was it. So I want to start out by giving you a little background. And there's my telling you what I'm going to tell you chart. So I want to give you some context for why did we think about this stealth program, why was it important. I want to place that into something that was developed that was called the offset strategy for dealing with the superior size of the forces of the Soviet Union and the Warsaw Pact post-World War II. And then I want to spend a minute telling you what stealth is and what it isn't, so you have some base of understanding. And I want to talk then some about radar and why radar is so important. In the context of human performance that this institute is interested in, radar was an enormous enhancement in the human's ability to know what was going on in the sky, when aircraft were there, where they were, and the ability to get after the aircraft. I'll show you a couple of photos of what we did to enhance human performance before radar, and I think you'll find them pretty laughable, but they were the best that we had. The Soviet Union got enormous leverage from radar. It was really developed in the US and the UK during World War II. We set up some very successful laboratories in Boston, the radiation lab at Harvard and a related lab at MIT. I've seen the Russian textbooks, and they all copy from those volumes on radar. But they spent, in my opinion, if we put it in US dollars, US equivalent work, pretty close to $1 trillion over 2 or 3 decades on radar, radar-guided missiles, and all other air defenses. And the reason stealth was important to us is, given all that investment, we thought we found a way to negate that investment at a much smaller price. And I think part of that was behind the eventual collapse of the Soviet Union. So then I want to show you some examples, some photos of what it was that did this, what made the difference, and talk a little bit more about what were the challenges, how we did it, what was the impact when we applied this in war, and how a small team of people was able to make a difference and bring this about. Okay, so let's start on this journey here. Offset strategy. At the end of World War II, we made a great reduction in our armed forces. Took it down probably by a factor of 10. The Soviet Union and Warsaw Pact didn't. They kept very large forces in place. So our strategy was to offset those forces by developing nuclear weapons and to use that as a deterrent. And that worked pretty well for a number of years until the Soviet Union caught up with us in nuclear weapons and made and deployed just as many, in fact, in some cases, more tactical nuclear weapons. So at that point, they had us matched to nuclear weapons, and they had a far larger force. And so our issue was, well, how could we deal with this? Because we didn't want to grow that kind of an armed force and sustain it through the period. So some very bright people that I worked with, then Secretary of Defense Harold Brown, and his Undersecretary for Acquisition and Technology, same job I later took, Bill Perry, did some work to develop this offset strategy. And the idea behind this was to leverage a smaller force by giving us better ability to find the bad guys and to locate them carefully. And that was work that we today call ISR, Intelligence, Surveillance, and Reconnaissance. And interestingly enough, much earlier in my Air Force career, I had responsibility for developing one of those systems. It's a fact of this has now been declassified, producing something called the synthetic aperture radar, which is up in space, but it's able to see, identify, and locate objects on the ground, and it's able to do that day, night, and through the weather. So it's very useful for this kind of purpose. Second thing that went into this strategy was something called PGMs, precision guided munitions. The idea here is one weapon and one target. A weapon is that precise enough that we're not having to distribute area weapons around. Interestingly enough, also, one of the first things I worked on in my Air Force career were our first television-guided air-to-surface missiles, to be able to make direct hits on objects using a television camera in the nose of the missile. And we've since improved on that a great deal. And then the third thing that we hadn't developed was stealth aircraft, because we were still dealing with these massive Soviet air defenses. And we had to find a way to get aircraft and munitions through those defenses to be able to carry out the strategy. So we decided to look a little harder at stealth as a means to do this. Okay. What stealth is not. So if you were coming here expecting to see the invisible airplane, I don't have one of those to show you. But I will say that this is illustrative to a radar system that was looking to detect or destroy this aircraft. The aircraft looks close to this. Pretty hard to find in the radar spectrum. And I'll go through a little more detail about strengths and weaknesses and limitations here. But I wanted to start to give you some sense here of what we're talking about. This was our first stealth operational airplane, the F-117 Nighthawk. We built 59 of these. I'll show you a few more photos later. And I'm not going to talk about the details of stealth yet, but I want to show you some unusual features. One of the things you'll notice is that airplane is built of a lot of flat surfaces. Actually, there are a lot of flat triangular plates there. And we found through experimentation that those plates were very good in doing the following thing. When the radar energy came in and hit one of those plates, rather than going back to the radar so the radar could detect it, the plates deflected the energy in another direction. So it did not go back to the radar. So when the radar is waiting for a return, nothing there. We also found an interesting Russian physics paper that solved these complicated radio frequency equations, the Maxwell's equations, in closed form for triangular flat plates. And they showed theoretically that the returns were very small. So that gave us some interest in looking at this further. You'll also see, I think, that this aircraft has a lot of unusual features. For example, things like the exhaust. Rather than a nice circular exhaust, what you see is that thin sort of strip. That was designed so radar energy couldn't get in there and come back out of the tailpipe. You'll see that the inlets for air, they have grids in them so that air can get in, but the wavelength of radars of interest couldn't penetrate into those grids. There's some other unusual features that I'll also come back to, but I just wanted to show this to give you some sense about what we're talking about. This is a tactical aircraft, F-15 size, capable of carrying two 2,000-pound laser-guided bombs to the target, and able to fly about 500 nautical miles and then return to base. And it was air refuelable. Now, radar. I promised to say a little bit more about this. Before we had radar, that is a US unit early in World War II. That was the acoustic equipment they were looking to identify the fact that aircraft were in the sky. And as you can imagine, it was pretty crude in terms of identifying where those aircraft were or what the tracks were, but it was an alert to be able to send forces up to intercept them. Acoustics were much better than the eyeballs, given the range and given weather and given night. And we weren't the only ones. Here's a man-aided system in the Warsaw Pact. I've got about 10 photos of this type, and it is amazing the Rube Goldberg machines that were made to be able to find aircraft. Okay, then radar was invented, and pardon a little bit of technical here. I'm going to only describe part of this chart now, and it'll come back up later. But what I wanted to show you here, if here's a radar transmitter, the little antenna that I've shown, the way radar works is it sends out waves, these little circles that are propagating out. And so they propagate out, and if there's something in the sky, like an aircraft, like this arrow, they hit that arrow, and then based on the size of that object, something we call sigma, the radar cross-section, how much area it effectively has, the signal bounces back. And again, we have these little circular wavelet patterns that send energy back to the target. I'll save the equations for right now. I'll come back to them in a minute. But why would this kind of capability be important? Well, one of the reasons is it works in all weather conditions to be able to detect that there are aircraft there. Another is that it has very long-range detection and warning capability, 100 times what the human eye can do, tens of times or more better than those acoustic systems. Next thing it does is it has the ability to precisely locate the objects, to give you the range, and by using a beam here to give you the azimuth, and by using a different beam scanning vertically, something called a height finding radar, to give you the elevation. And once it has all that information, it can then keep track of it to give you the track of the aircraft. And then the next piece of this was kind of invented post-World War II, but soon thereafter, is the ability to hand that off to a missile that can be launched. And the missile itself has a radar in it, which can keep the track and guide itself all the way to be able to arrive very close to the target aircraft, to an intercept point, and then that missile has a fuse which causes a warhead to detonate to knock the aircraft out of the sky. So these were all put together into complete radar and fire control systems. These were the devastating systems that took down so many of our airmen in Vietnam. One of my motivations, actually, to work on this stealth program, I had nearly 5% of my classmates in my graduating class at the Air Force Academy end up either deceased or prisoners of war in Vietnam due to one of the Soviet systems that I'll show you in a minute. So radar is really extraordinary for this air defense job by putting together all these features, and it was probably the biggest, most important invention in World War II, save the atomic bomb. But it was pretty close to being right up there in that class of important things. And the advantage of stealth is to make those things go away. I want to just illustrate a few of these systems for you. This is one of the major Soviet radars that's used for missile guidance. It has an antenna here to track the target. It needs this antenna here to illuminate the target for the missile to follow that signal and guide. It needs 5 other radars for detection, tracking, finding the azimuth and height before it can even work to lock on the target. Big and expensive system. Now this system provides then the guidance information for this missile. This is probably one of the biggest, most effective Soviet surface-to-air missile systems. This is a huge missile. It's 35 feet long, 3 feet in diameter, if you think about that for a minute, weighs over 15,000 pounds, dual thrust rocket engine, can fly 250 kilometers. So, and the first version went up to 65,000 feet, and when we developed the SR-71, they extended it to go up to 115,000 feet. This had 6 launchers per battery, multiple missiles per launcher, and by 1985, the Soviet Union had 130 sites with nearly 2,000 launchers in place. I think you get some sense of the scope of the program that they put together to defend their country. Here's another missile, SA-2. This was the missile that shot down Gary Powers' U-2 aircraft. For anybody who flew in Vietnam, this was also the nemesis that you were all usually looking for, the so-called telephone poles that you'd see coming after you. Very effective in both theaters. Hundreds of thousands of these were built and deployed in the Soviet Union and in the Warsaw Pact. This is an SA-3, smaller tactical systems. One of these systems was actually used to bring down the only F-117 that was ever brought down in combat. And it was brought down because we got too confident about the capability of the aircraft. And we were operating it in Serbia in a repeating pattern, flying over the same places so somebody could watch the takeoff and predict that in 13 minutes this aircraft was going to be in the following place. They placed an SA-3 right at that place, and they were able to take down that one aircraft. It's the only one we lost in all of the combat missions that we performed. Another one, SA-6. These numbers now go all the way up through 20. And then give you a feel for the deployment. Those big missiles that I showed you to start with the big Raider, the SI-5s, these were all deployment sites that had multiple launchers all around the Soviet Union. And then in Moscow, just pick one city. Let me give you the scale of this. Moscow is right in the middle. And this white ring that goes around Moscow, that's a little bit bigger than the Beltway in Washington, D.C., to give you some feeling for scale. And then every one of the red dots is a site, a missile site, that had somewhere between 6 and 12 launchers. So, I mean, just putting together this defense of Moscow is a huge expenditure. And then you think about the people to man it and to sustain and operate this was a huge, huge expenditure. But the Soviets were intent on defending their homeland. We took another approach. In the 70s, we decided air defense of the United States with missiles and radars on the ground was too expensive. Maybe some of you are old enough to remember the old Nike sites that we had, or places around the country. We just decided we couldn't afford to keep doing that. We had to find a better way to do it. So one of the better ways we found to do that was to invent this system called the AWACS, an airborne warning and control system. And what we did here was put the radar in this antenna, which rotated on the airplane. Now the advantage of that approach is one of those aircraft up in the air at 30,000 feet could cover a circle of a little more than 250 miles in radius. So 4 of those systems could cover the entire East Coast. And we built a total of 34 of those and also built some for our NATO allies. Now, those systems weren't designed to destroy, they were designed to find and then to pass that information off to an interceptor that was airborne or in areas where we had limited ground-based defenses to hand off to those systems. Well, like in other areas, the Soviets soon followed, about 10 years after us, fielded a similar kind of capability, keeping radar still in the game. So I want to go back to this chart I promised to come back to. Now, people had thought about stealth before us, but they were deterred by the following problem that comes down to basic physics. Remember, I was describing that the energy goes out in these circles, and actually, if we are thinking about this in 3 dimensions, it's going out in spheres, if you can think of an expanding sphere. And those of you who remember your high school math will remember that the area of a sphere is 4 pi r squared. So as that energy goes out, the energy dissipates like 1 over 4 pi r squared. It becomes less intense as the sphere is spreading out because it's being distributed around the whole surface of the sphere. So as the energy comes out to hit the target, when it gets out to a distance r, it's 1 over 4 pi r squared as strong as it started. And then when it hits the target and gets reflected back, these little rings, it's also getting reduced by 4 pi r squared again. So if you looked for an equation that describes the size of the radar return, it's my only equation. It's a constant times sigma, the radar cross-section or signature of the object, divided by the radius to the 4th power. So if you look at this, you get discouraged about stealth. Why is that? If you want to reduce the detection range by a factor of 2, 2 raised to the 4th power is 16. If you want to reduce it by a factor of 4, it's 16 squared, 256. So if we looked at a large target here, like a B-52, radar cross-section of maybe 600 or so square meters, if it were detected by a radar at 160 miles, if we wanted to reduce that detection range, say to 20 miles or to 10 miles, taking it down to 10 miles would require a reduction of 60,000 times in the signature, getting it from 640 to 0.01. So most reasonable people looked at that and said, no way that you could do that. So let's look for something else. We'll apply electronic countermeasures, which we did. But there are a group of us who looked at this and said, that might be feasible, and let's go do a little more experimentation. So we did that. We built some models, we made some measurements, and we were encouraged enough to build a test airplane. And we were encouraged enough because for a defense to be effective, it's not just a matter of detecting an object. You have to do all these things. You first need to detect. Then you need to locate. Then you need to be able to track the object. Then you need to be able to hand off to a missile system that acquires it. You then need to launch that missile. You then need to guide the missile. The missile then needs to fuse to set off the warhead, and then the warhead needs to damage the target. We call this the kill chain. And in the stealth program, what we decided to do is see how many places we could break this kill chain with our reduced signature. Could we apply stealth and proper routing to either avoid detection or to greatly reduce the detection range so people didn't have time to react? Could we apply stealth and some maneuvers of the aircraft to create location errors and break the track? Could we apply stealth to limit the reaction time so there wasn't time to be able to acquire the target and launch the missile before we were by the target? Could we apply stealth to reduce the guidance capability, to increase the miss distance? And could we even apply stealth to cause the fuse, not to detonate the warhead? So we did careful modeling and simulation work and testing on all of these pieces to verify the models. And we decided this was worth a shot. And so in 1976, we built 2 of these aircraft. The aircraft were not mission capable. They were only designed to do one thing, to see could we build an aircraft that had those kind of signature reductions. And the way we had to do this was to not think about building an aircraft. You had to think about building an antenna. And what you had to think about is building the worst antenna that anybody had ever built so that none of the energy would come back to the radar. And then every now and then check to see, could it fly? That's exactly what we did. So this was not a proud flying machine, but it was a very poor antenna. And so what we did was modeled and predicted the signature, and then we took it up in the air and measured it. And we were encouraged. And to accent the fact that this was not a very good flying machine, we built 2 of these aircraft. We crashed 2 of these aircraft. We got about 30 flights out of each one. And at the time that program was ending, I came on the scene. This had been started before I was in the job and where I got assigned to look at this. And I was newly assigned to work for the Undersecretary of Defense, Bill Perry, who was a very bright guy and was interested in this. He asked me to take 3 weeks and come back and tell him if I thought we could actually do this operationally. And I looked at that, and I saw all kinds of challenges, but I also went back to that kill chain I showed you and showed you all the places where I thought I could muck with the defenses. And I came back and I told them I thought we could do it. So in 1978, just after we finished all these flight tests, we approved this program, which is the F-117, now nose-on. We awarded a contract to build 5 R&D aircraft in November of 1978. In 31 months, we had the first one flying. And in October of 1983, just a little, around 5 years from when we first started this effort, we had the first 10 airplanes operational for a limited operational capability. We don't do things in that kind of schedule today. Here's a view from the top. The aircraft was air refuelable. You can see what I was talking about, the gridded inlets. This aperture here was a forward-looking infrared system. We had another one on the bottom to find targets because we did not know how to make a radar for this aircraft and to make the radar emanations not detectable. Didn't want the radar to give away the position of the aircraft. This aircraft had a lot of fancy features. I'm not sure if you can see them. There are 4 sort of straight lines sticking out, one right on the nose, 2 here and 1 there. One of the aerodynamic disadvantages of this stealth work was that it was very hard to design aircraft that were statically and aerodynamically stable. To make an aircraft stable, you have to have the center of pressure behind the center of mass, because the center of pressure is pushing up to lift the aircraft. If the center of pressure is ahead of the center of mass, when the aircraft pushes up, you get more lift, and that's a bigger push that pushes the nose up more, and what happens to the airplane? It departs and goes into a spin. Unfortunately, in all of these aircraft designs, the center of pressure had to be ahead of the center of mass. So how do we fix that? We put these 4 sensors out there to sense angle of attack and side slip. We used 3 of them at a time in a majority voting scheme with a computer for each to compute the correction that we need to keep the airplane flying on the flight path that we wanted, and then we closed all the flight controls through that loop. Without those flight controls, the airplane would depart. So that's why we had 4 probes, so we could have 2 sets of 3 voters. And when we lost 1 probe or 1 set, the airplane had to come home. It was still safe with 3. But the airplane absolutely relied on those for its stability of flight. And it took some tricky computer work to make that all happen. Another view of the aircraft, you can see that exhaust that I had spoken about earlier. This is closed up now from the air refueling mode that was in. Airplane maneuvered reasonably well, but this is not a dogfighting airplane. Now, to be useful mission-wise, you have to be able to carry and deliver weapons. So there's some fairly sophisticated work needed to be done with those bomb bay doors and opening them up and making sure they sealed properly after weapons were dropped. And we also did our homework in making sure we had the right weapons. These are 2,000-pound laser-guided bombs. There's a laser underneath the aircraft that would illuminate the ground, illuminate the target, and the bombs would home in on the target. And these were weapons designed actually here at Eglin Air Force Base to be able to penetrate about 30 feet of steel reinforced concrete. We used these the first day of the war in Iraq. There was a key command and control center buried about 60 feet, maybe 75 feet underground. It was the nerve center of the Iraqi integrated air defense system. So we put one of these on that defense system, and it went down, blew a hole down to about 35 or 40 feet. We put a second one in the same hole, took it down to 70 feet, and took out the eyes and ears of the Iraqi air defense system. There was our first operational unit. They were based covertly at a base in Nevada. Pilots flew there on temporary duty to fly their missions. This unit was the first 20 that we built. And then when we deployed the unit, it looked something like that. These were deployed to Saudi Arabia just prior to our launching Desert Storm. That was the first generation of stealth. I'm going to still kind of keep on that subject, but I just wanted to show you where things went next. As we were building that airplane, we really didn't like those flat plates and sharp edges from an aerodynamics point of view. We had to give up too much in aerodynamics performance for other than a narrow mission. So we looked at another approach to this. This This aircraft here was fondly called the Whale for obvious reasons. You can actually see that this aircraft is at the museum at Wright-Patterson Air Force Base, if you're ever there. It's called Tacit Blue. And we had two purposes in this aircraft. One is to show that we could get these small signatures without using these triangular flat plates. We discovered mathematically that if we used Gaussian curves, same curve you have in a normal distribution, mathematically those curves have infinitely smooth derivatives, so no sharp edges. And we found out that Maxwell equations like those also for small returns. We also did another thing on this airplane. We put a synthetic aperture radar in the side there. We had figured out a way to code the radar energy that went out so that you couldn't see the radar energy unless you knew the code. And we knew the code, and somebody trying to find the aircraft couldn't find the code. We needed a radar like that before we considered building the B-2. So this aircraft was sort of the precursor, the proof that we might be able to do something like a strategic bomber using these curved surfaces and get back all the aerodynamic performance and being able to put a radar in the aircraft. So that led to the B-2, which was the next aircraft we built in the program. Now, this is an aircraft that has a range approaching 3,000 miles. And when we used it in Afghanistan and in Kosovo, we would operate from its base in Missouri, fly it from Missouri halfway around the world where it would drop its weapons, one refueling en route, turn right around without landing, and fly back to the United States. So it had excellent aerodynamic performance as well as good signature performance. And it was able to carry 16 of those 2,000-pound bombs, or 80 of our GPS-guided JDAM 500-pound bomb munitions. So an extraordinary capability. I want to stop now, and I've told you everything here above the line. I promised to give you a little sense of the impact of stealth, so I got a little bit of part of the war report in Iraq to go back and share with you. So on August 20th, 1990, we had KC-10 air refueling aircraft from March Air Force Base join up with 22 F-117s to take the 15-hour trip across the Atlantic. Required 7 refuelings. We also sent 4 spares from that 22 back to Tonopah because we only wanted 18 in the theater then. So that left 18 in Saudi Arabia at the base that I showed you. They were there preparing for Operation Desert Storm. On December 2nd, we sent the second installment of another 20 F-117s from Langley Air Force Base, and 18 of those 20 continued to Saudi Arabia. So we had 36 in place. So on the first day of the war, I just captured this report from the first person, Major Salata, who dropped the first bomb in Operation Desert Storm. Salata bombed Baghdad's Sector Operations Headquarters, their air defense nervous system headquarters. The center which directed all of the Iraqi air defense fighter aircraft at H-hour -3 on January 17th, 91. A few minutes later, he made the following radar call. In the call, he reported that the first raid here with 10 Nighthawks was so unexpected that all the city lights were still on. The practice would be to turn those off during detection of an air raid. And he said the early attacks along the next few waves knocked the eyes and ears out of the Iraqis so that they were blind and deaf. Now I want to go to a summary of the whole war and the operation. The F-117 proved invaluable in the Gulf. In the first day of the war, 36 F-117s, less than 2.5% of the UN coalition tactical assets, were in the theater, and those 2.5% of the assets attacked 31% of the targets that day. Without the F-117 striking Baghdad, what we would have been facing there with the rest of our coalition aircraft were 7,000 radar missiles, 9,000 IR missiles, and 7,000 anti-aircraft guns and 800 fighter aircraft. So that was all wiped out by taking out the eyes and ears. In the total Gulf War, the F-117 flew 1,300 sorties, with direct hits on 1,600 high-value targets, delivering 2,000 tons of precision-guided munitions with an 80% success rate. So we were very happy with that performance. Next, when we went to the B-2, here we had an aircraft with 3,000-mile mission radius now, and the ability to carry 16 of these 2,000-pound weapons, or 80 of 500-pound guided weapons with an air of about 10 meters. And they were launch and leave. A good friend of mine, Ron Fogelman, who was Air Force Chief of Staff, gave a nice little summary that I'd like to repeat briefly. He said, by comparison, during World War II, the 8th Air Force attacked something like 500 target sets in all of the year 1943. During Desert Storm, the coalition struck 150 individual targets in the first 24 hours. Not too far into the next century, with the B-2, we may be able to engage 1,500 targets within the first hour, if not the first minutes of a conflict. Gone are the days of calculating aircraft per target kinds of ratios. Now we think in terms of targets per aircraft. So that was the change that, that this all brought about. So that's the impact. And then the next piece is, well, how did a small team of people do this? Ken started out saying that the office I worked in was called Low Observable Technology. Actually, for the first 3 years I worked in it, it wasn't called anything. There was no office. You couldn't find us. 9 of us in the Pentagon. Actually, there were 10 of us, and we had 9 desks, because there was always at least one traveling on the program. But what we did was put together a small team that integrated together industry, university expertise that we needed in modeling and simulating these activities, a tremendous test team who did all the testing in the field, and the industry who was involved. We had a monthly management meeting of about 10 people. And the price of admission to the meeting was we decided at the meeting. There's no going home to check with your boss. Some people couldn't do that. We had to replace those people. So we decided in the program, month at a time, what we're going to be doing in detail, and then looked at the overall schedule for 6 months. People ask me, well, did you ever make mistakes in meetings like that? Answer is absolutely right. All kinds of mistakes. However, never did I see a mistake last 2 meetings. And when you work with a group of people like that over a period of time, what you see is what I call the 4 Ps in operation. And everything I've been involved in that was ever successful had all 4 of these Ps. The first P is the people, most important piece of the whole process. Selecting a group of very able people, arming them with the tools they need to do their job, standing back, giving them the room to do their job, giving them the opportunity to make some mistakes, but stopping them from making fatal mistakes if you can, providing them with the education and training that they need. The second P that you need to make this work are partnerships. You have to have a group of people who are able to assimilate a common objective and to work for that objective in common. That's very tough today. And here I'm talking about not only the engineers and the program managers and the industry, but the university piece, the financial managers, the leadership in the Air Force and Department of Defense, the Congress. Developed a very special relationship with the Congress in this program, which worked extremely well. Able to bring about compromises of the kind that are very rare to see today. Processes. The use of this kind of integrated product team. The development of modeling and simulation. I wouldn't let us do a live air defense test without having the prediction of our models beforehand. When we started doing that, our models were terrible. We'd make a prediction and the real test wouldn't look anything like that. And what we learned is we didn't have all the right things in the model. And over a period of time, the models and the test results started to agree. The models were then critical for how we routed the aircraft. The models were very critical to giving our crews confidence that when they saw a missile launched, they were not to turn and burn. That's the worst thing to do in this airplane. You need to fly straight and level. How do you build the confidence in a crew to do that? You do that by showing them the modeling and simulation results, then you do it by taking them out to the range and say, okay, you go at it, you do what you'd like to do, see what happens, and then do what we ask you to do, see what happens. And if you do that enough times, you develop the confidence to do what you should do. And then the last P is persistence, staying with it. Because all kinds of problems develop in programs like this. And if you're persistent, you'll find solutions. I could share a few of them with you, but we're probably running out of time a bit. Well, let me close this with just a couple of more photos. That's one of the senses of a partnership there. That's an extraordinary group of people. This photo is labeled the fathers of stealth. Anything that's successful is going to have many fathers, and there are many more than this who contributed to it, but this is a great group of guys. This fellow right here, I don't know if any of you know him or recognize the picture, probably not. His name was Kelly Johnson. Kelly designed a couple of aircraft. He designed the P-38, the Lockheed Constellation, the U-2, the SR-71, just a few aircraft like that. Extraordinary system engineer and designer. Kelly handed over the skunk works to this guy, Ben Rich, who took over that operation during the F-117 program. Person back in the corner here is Hans Mark, who was Air Force Secretary and then later a NASA Director. Person right here is Lou Allen, who was Air Force Chief of Staff. This is me in my younger day. This is Bill Perry, who was the Undersecretary of Defense at the time, and this is Ken Staten, who was the manager of the 117 program. A great team of people who worked together in a reinforcing and positive way. I didn't have the opportunity to fly in the 117 when I was on active duty, and we hadn't yet finished developing the B-2 when I retired in '84. So sometime after I retired, I was invited to take one of the early flights in the B-2, and easiest airplane to land I've ever flown. Great flying airplane. And remember those sensors I told you about on the F-117, those probes that stuck out? Well, here are the 4 that were on the B-2. So there's some limitation here associated with stealth as well. For example, some of those conditions. The signature reduction I talked about can't be achieved at all frequencies. Some people are moving to frequencies where they can better find the aircraft. Every one of these actions that you take has a reaction, and so there are reactions in place today. But when you look at the big picture here, as I said, the Soviets spent hundreds of billions of dollars, perhaps $1 trillion, in deploying those air defenses. We spent $5 billion to develop and build the first 59 F-117s. We spent more than that on the B-2. Close. It was nice to get some presidential recognition. Wonderful man who took great interest in this program. And unusual, I ended up getting that that letter from President Reagan on the day I retired from the Air Force. And again, that letter came to me, but let me assure you, this wasn't me who did this program. This was a team of people. Thank you.
I was wondering if there's a successor to radar on the horizon that you can envision.
One of the successors to radar are improved radars, putting out more power, putting out some different waveforms. Also, infrared technology is coming along to be able to do a good job, and it's harder to reduce the signature of an aircraft that's flying up against a dark sky when looking at sensor from the ground. We have infrared sensors today that can see aircraft there. But the problem with infrared sensors is weather, moisture in the atmosphere. You know, they have their limitations too. I would also tell you something else. One of the early things I did in this stealth program was worry a bit about was I right in terms of we could really do this and it would be sustainable. And so one of the things I did is took a couple of % of my budget and I put together the 2 best red teams I could from industry. One team I gave all the actual performance data of the aircraft, all of its signature. Another team I gave them only what I thought the Soviets might know about the airplane. And I asked them to do their best job. These were the leading air defense companies in the US. Do their best job of reacting to be able to destroy these aircraft. And I did that for 2 reasons. One, because I thought, given the amount of money we were about to spend, we ought to have several minds looking at this problem and to see if they could find weaknesses. Secondly, if we were going to field this, just like the AWACS, it was only going to be a matter of years before the Soviets would try to field something like this. And so we ought to use this data from the red team to find where the biggest weaknesses were and start investing in the technology that we would want to have a leg up in dealing with it. So we did both of those. And it was very, very helpful to have that information in running the program, too. The red team work is great, and it was a very important piece of that process that I forgot to mention. Yes?
I've been led to believe that the paint composition had something to do with low observables. Is true. Is that correct?
The paint itself doesn't do much because it isn't thick enough. But there is absorbing material that we've developed of various sorts to be used in the right kind of places. And you can also imagine if you have apertures on the airplane, you know, what you're really trying to do with this airplane is to make a gentle transition. It's a hard transition from the electromagnetic characteristics of air to metal. But if you can make this transition happen in small steps, you can now greatly reduce the reflected energy. And so what you're trying to do is produce a material that will do that, make that transition happen in steps, and if it can, absorb some of the energy in the material while it's doing that. Yes, sir.
Is there a potential for satellites to pick up aircraft, and if so, specifically this type?
Yes. The satellites, those suffer the same kind of problems that the radars do. To see these small signature aircraft, they have to use a lot more power. And the satellites then have another problem, too, which the AWACS also has. And in the interest of time, I didn't go into this. I showed you the 1/r⁴ problem that we have with sensitivity. There's only a 1/r² problem if you're trying to get lost among the clutter in the background. And if you have a radar on the ground looking up in the sky, you don't have to worry too much about clutter. But if you have a radar up in the sky looking down at the ground, you're getting big returns from the ground. And it's hard to find these aircraft in the middle of those big returns. You have to really do some very fancy signal processing. Well, you can do that, but it isn't as easy as it might first sound. Let's see. Jim.
First question, when did you sleep based on your resume? No.
You know, I've been very blessed. I've had the opportunity to really work on some interesting things. I just seem to fall into these things. You know, my work on precision-guided munitions was really fun work. In fact, spent a lot of time right near here doing that. What we did was outfitted a C-130, put 2 Vidicon cameras in the nose, and then flew against all the bridges around here while we were trying to knock down bridges in Vietnam and looked at the best guidance schemes for TV seekers. The National Reconnaissance work was great, and then I actually am still blessed to be involved in some of our major national programs.
My serious question is, can you talk at all about the F-35?
Yes, I can.
Because it might be of interest to people since it's stationed at Eglin.
First off, my bias. I started the F-35 program when I was Under Secretary of Defense. You know, no one would ever want to say there are any ugly aspects about their baby. But I think what we're seeing right now with the F-35 is something that will end up being an extraordinary airplane. And I don't think the stealth will be the most extraordinary feature of the airplane. I actually think the fusion of information that aircraft will be receiving and generating on its own and putting it all together in a fused manner will be every bit as important. Every aircraft program of that size has these kind of growing pains and eventually stabilizes. This one hasn't stabilized completely yet, I don't think. And because one of the challenges you always face in a big aircraft program is you got a few thousand engineers, and you don't have everything tested yet. And you want to start building some airplanes so that you're testing what you're building, not just a few R&D airplanes. And so you always end up with this problem of, well, how fast should I build the airplanes? Because every one that you build, when you test it and you find out it isn't right, now you have to go back and regress and make changes to all those aircraft. If you don't build enough, then you're not testing what you're building. So you're always in this sort of dilemma, and that's where we are still with the F-35. I'd also say another thing. I never envisioned when I started the program having our whole fleet of tactical aircraft equipped with those stealth airplanes. I mean, one of the penalties of stealth is you don't have the flexibility to carry the number and weight of external weapons. You don't need all this capability day 50 of the war. You need it first 10 or 20 days. And so we need some balance in what that composition of aircraft is.
Time for one last question.
I was just going to ask that, given the lead time from when you first started working in this to the common knowledge or practical application as far as the public was concerned was a good many years, 15, 20 years?
Not that long. I would say only maybe 7 or 8.
Well, it just, for those of us who are out here, makes you wonder what all's in the pipeline. So you don't have to address that, but it does.
Let me just say that you have some very good, capable people working just as hard as this team I had, and there's some good things in the pipeline. But I would also say they have a much bigger challenge than we have today, because everybody wants to fix this acquisition system, and if you add enough rules to the acquisition system, failure won't happen by chance. Because if you have to comply with all of those rules, every rule is intended to stop some problem that we had in the past. And people don't realize the opportunity cost of all those rules. We're all human. We're all going to make mistakes. You have to have room to make some mistakes. Congress wants things to be perfect. No mistakes, no errors in the program. And humans don't do that.
Not humorous enough. Congress wants perfection.